Do you remember one of our very first units of the whole year? Like chapter 1 or chapter 2? No, not at all. Very first topics we went over. Yes. Thank you. That's good thinking. All right, so we started with kinematics. What did we go to after that? We did a little projectile motion. Okay, that won't necessarily apply here. We did some circular motion. We did forces. We did our free body diagrams and forces. Then we did conservation of energy. And then we did momentum. And we're going to do all of that all over again, except this time in a circle. So we're actually going to start with kinematics today. So this will actually be similar to what you already know, except we're going to apply the kinematics to things moving in a circle. So instead of talking about like a linear distance x, we're going to talk about an angle that something might sweep out. So in our next equation quiz, we'll have the regular kinematics and the rotational kinematics. And they are the same, but we have different rotational variables. But theoretically, if you remember one set, you should know the other. And how do you measure angles in like pre-cal? Radians. Okay, so we've studied translational motion so far, basically straight line motion. Now we're going to study rotational motion. I know we have studied circular motion a little bit, but we're going to study it more in depth, and also referring not just to like a point going around in a circle, but say, a whole actual shape, like maybe a record or a CD or something, or whatever that's supposed to be. So we do have the correlation between rotational and translational, and every time we learn a new formula, we'll kind of relate it to what we've already learned. But just as we had displacement, in the x direction, we also can have angular displacement. So we'll have theta here. We have velocity. We're going to have angular velocity. Just basically stick the word angular in front. That's going to be lowercase omega, kind of like a W. And angular acceleration. That's going to be alpha. So we'll just go through each of those real quick. Angular displacement, just simply the angle you would sweep out. So this is another formula that would be helpful. The angular displacement is arc length over radius. So that would be S over R. And if you do S divided by R, please realize that that will be an answer in radians. So we do have to pay attention to whether we're given things in radians, in degrees, or maybe even like sets of revolutions. Was it 5 full revolutions? So we have to pay attention to our units, as always. All right, 240. Okay, and we're just using our formula that we already know for displacement. Displacement is final minus initial. It just happens to be angular displacement is final angle minus initial angle. So page 240, checkpoint 1, it says the disk in the figure can rotate about its central axis like a merry-go-round. Which of the following pairs of values for its initial and final angular positions, respectively, give a negative angular displacement? So in which cases will this be negative? Very good. Just final minus initial. B, you'd have -7 minus -3. That'd be negative. -3 minus 7? Sure. B and C. Piece of cake. All right. Calculators, help me with this one. Or maybe you just know this one from your unit circle, but again, pay attention to what units you're in and what units you should be in. It's pretty easy to go back and forth from radians to degrees. Do I have my, yeah, here's your little unit circle. Hopefully remember that, you know, a full circle 360 degrees is 2 pi radians. So I often just use the relationship that 180 is the same as pi. So 15 degrees is going to be how many radians? What is that divided out?
0.262.
There we go.
Are we going to keep the radians in decimals always?
Yeah. Well, that's like half and half. Sometimes it's in terms of pi, sometimes it's written out in decimals. Your multiple choice will almost always leave it in terms of pi. All right, so angular displacement, angular velocity. You know what velocity is. So it's just simply how fast do we sweep out that angle. So just like, you know, regular velocity is displacement over time, it's just angular displacement over time. And just like we could do the derivative, when it was linear, we can do the derivative here. SI units be radians per second. And then lastly, acceleration. So the rate of change of angular velocity. So that could be like, you know, a record player, as soon as you turn it on, is of course speeding up. What is that rate of acceleration? Okay, and just like we learned in chapter 2, if acceleration is constant, that's when we can use the kinematics. If acceleration isn't constant, then perhaps that was a case where we needed to do derivative. But if it's constant, we can use the kinematics. So quickly go to 244. It's just asking, when can you use the kinematics? So checkpoint 2 on 244. In 4 situations, the rotating body has angular position theta, given by all these equations. To which situations do the kinematics apply? So how would you figure out if acceleration is constant given those formulas, or those equations? You're given theta, which is angle. Good, second derivative. So what's the second derivative of A going to be? Good, 0. How about B? Okay, so there's a t involved, yeah, plus some other stuff, or plus a constant, I guess. If we have a t involved, is the acceleration constant? Nope. How about C? We got t to the negative 2. So no, t is definitely still going to be there. And how about D? Yeah, that would work. So A, except that acceleration is 0, and then D. Just take your second derivative. All right, so here are all our friends again in code names. Just notice how they apply. Not really sure why we switched to using F instead of the not, and it doesn't really matter.
Can we use not?
Yeah, you can, if you wanted to change this to like omega not, and then leave that one as just omega, that's fine too. All the same kinematics. Do note at the bottom, I know I'm mentioning that we'll likely be dealing with the angle in radians, and especially if you're using that arc length formula, you would get an angle in radians. But that doesn't mean your units have to be in radians. They just have to match. So this could be revolutions per second. This could be revolutions per second squared. But you can't have revolutions in some and radians in others. All right, now how do we describe vectors? Because these are still vectors when you have a constantly changing direction, something moving around in a circle. And we have the coolest rule of all time. So I love watching you guys try to do this. Anyway, you'll see. Maybe my merry-go-round will work for this. Yes, and it is also sad when the left-handed students do it wrong. Okay, so here's my Kinex merry-go-round. It is moving slowly. It has an angular velocity. What direction would you say that angular velocity is in? What?
To the right.
To the right? Who's right? That right? That right? That right? That right?
Mine right.
Exactly. So that's the problem with saying like right or left. What point are you talking about? Whose reference frame? So if you have an object that's rotating, you take your right hand, and it does have to be your right hand, or if you're left-handed, switch it. Switch your answer. And you curl your fingers the way the object is curling, or moving, basically. So if this is rotating like this, I'm going to curl my right hand, and I would say the angular velocity is up. Then anyone else can take their right hand and say, okay, thumb's got to be up. Look at my fingers. Oh, it must be spinning like this. So it's one direction that does describe how your object is moving. Same with this object right here. If it's spinning sort of counterclockwise, then that will be up. Now, of course, we could have things at different orientations. But it is a lovely system for explaining the direction of things that are moving in a circle. There should be an N there. I think my little hand is over it. But your thumb points in the direction of the vector. Okay. All right, a couple of examples. How many slides until Lisa Simpson? All right. Not too shabby. Okay, so the angular position of a swinging door is described by that equation. Determine the angular position, angular speed, and angular acceleration of the door at these specific times. Easy, we've done this. What do we got to do? Plug in and derivative again. Okay, so let's start with theta. Theta at 0 is going to equal, do that in our head, right? 5. Okay, now what unit? Good, it's in radians. All right, theta at 3. $53? Okay. Easy. Next. Angular speed, so that's going to be omega. Well, let's just get omega first. What is the derivative of that? Okay. So then omega at 0 would be just 10. Now 10 what? Very good. What do you got? 22. All right, and last one. Alpha is just simply 4. Doesn't matter what time then. And as before, what? Very good. Always. So that is a case where alpha is constant. We technically could use our kinematics if we needed to. All right, good. We remember how to do derivatives. What are you guys studying in calculus these days? Have you done integration with trig yet? Like sine, cosine? Okay. We need to know that at the very last unit we do. All right, another example. Wheel rotates with a constant angular acceleration of 3.5 radians per second squared. Okay, so that is like immediately our hint that we can use kinematics. If the angular speed of the wheel is 2 radians per second at t equals 0, how many rotations will the wheel have made after 2 seconds? Okay. First question, what's the question? How many rotations? What variable will we be solving for there? Theta. We're really going to solve for the angle and then figure out how many circles that is. Okay. Then we got 3.5 radians per second squared. Good. Just notice the second squared. That's definitely going to be our acceleration, but we're going to call it alpha this time. And what's the 2? More specific. Good. That's our initial omega. Call it omega naught, omega I. And we have time. Excellent. All right. What kinetic?
Theta equals omega naught t plus half of alpha t squared.
Okay, that's got everything. Looks good. Do check your units. Okay, we've got radians. That's all good. Which just simply means my answer will be in radians. $11. Okay, that is helpful. It's not exactly our answer.
Well, I didn't get I didn't
Pi. So just figure it out and do 3 pi.
Divide by what? 2 pi. Good. You have your answer in radians. How many rotations is that? Well, that means you've got to know, 1 rotation is how many radians? Well, 1 rotation is 2 pi radians. So we've got to just divide this by 2 pi. That's a pi. I don't know what that is. 1.75. So, almost did 2 circles. We could tell. All right, a couple slides on relating our linear and rotational quantities. We're going to start with our arc length formula. And I'm just going to take the derivative of both sides with respect to time. And if we look here, the derivative of the arc length is essentially your linear distance. Yes, it's curved, but it is the linear distance. Let's say a point on the rim is traveling. So we're going to essentially call that the speed, the velocity. But don't actually call it the velocity because the direction is ever changing. So that is our speed. Over here, if we're taking the derivative of the angle, that we know is omega. That's our angular speed. And then, of course, r is still just there. R is r. I call this marching band equation because if you think of a marching band and they're making a turn, what is constant about everybody in the marching band? Is it their linear speed or their angular speed? If they're a good marching band, hopefully their angular speed. They're sweeping out the same angle in the same time. But who's got to walk faster? The people on the inside of the turn or the people on the outside of the turn? Outside of the turn. So that's why your linear speed is based off of the radius. The farther away you are, the bigger the radius, of course, the faster that person would have to be walking. So there's one helpful relationship. That equation makes sense? I like to think of it as a marching band equation. It's got another pair. This is the marching band equation acceleration form. I guess assuming the marching band just started to run all of a sudden. So we're just starting with this equation, taking the derivative with respect to time on each side. Basically gets us down here. Yes. And this is one slightly confusing part here, is that there are really three types of acceleration we will talk about in this unit. And we've got to make sure we know what they all mean. What does AT mean?
The kind that's in a straight line.
Right. This is tangential velocity in a straight line. So if I don't know, talk about this one little purple point moving from here to here. Its tangential acceleration would be this way. What other type of acceleration have we already studied? Centripetal acceleration. Okay, now that's due to a centripetal force. You know, I've got these interconnecting pieces, so there's some tension in these pieces holding this outer part together and keeping it moving in the circle so the parts don't just fly off in random directions. So that's centripetal acceleration. Please note that that is not what this is here. This is a tangential acceleration, like the marching band starting to run in its turn. And then lastly, we also have alpha, our new one. That's rotational acceleration. That's, you know, how quickly is that angle being swept out faster and faster and faster. So that's talking about just the angle itself. All right, and sometimes centripetal acceleration is called radial acceleration, like it's points along the radius. So AC and AR are the same thing. I think this chapter kind of switches over to radial instead of centripetal. Same thing though. But we're just doing another little substitution here. You can see I'm plugging in the marching band equation to our period equation. So our rate sort of cancels out there. And then here we took our, you know, our known centripetal equation and we plugged in again the marching band equation. But please don't confuse this one with the one you just wrote down. And here's a little summary of them all on the next page. Those all written or no? Okay. So these are all sort of the helpful equations that relate linear and rotational terms. And you'll be using some of these in the web quest we do tomorrow. And by tomorrow, I mean Monday. Oh, and this is important too, though. For the ones that relate linear to rotational, those do have to be in radians. Because radians is sort of like a blank unit almost. Like arc length, that could be in meters. Well, radius would be in meters too. That would match. Velocity is meters per second. This is radians per second, and then R would give you the meters. Still be meters per second. Okay, now we made it to Lisa. Okay, so imagine you have this little merry-go-round kind of thing with Lisa and a cockroach. I don't know why I put that on there. Maybe that relates to 246. Go to 246. Yeah, is it before or after? Okay. We can save that one for later. You don't really need it for tonight's, but we'll do that one. Be in class next time. Oh, there it is. Okay. It's like, why? All right, so 246, checkpoint number 3, says a cockroach rides the rim of a rotating merry-go-round, as along with Lisa Simpson. If the angular speed of this system, the merry-go-round and the cockroach, is constant, does the cockroach have radial acceleration? This is moving at a constant rate. Is there radial acceleration? Yes or no? One of them is no, but is radial no? Is it moving in a circle at all? Yes. Remember that this is the same thing as centripetal acceleration. So yes, if it is moving in a circle, the only reason it's moving in a circle is there's some force and some associated acceleration keeping it in that circle. In fact, what would be the force keeping the cockroach in the circle? Specifically what? Coming from what? Friction. If this was slick, a cockroach would go flying off. So even if it's moving in a circle, at a constant speed, there will always be centripetal or radial acceleration. Did I say it? Darn. Well. So, radial acceleration, yes, there will definitely be some. Okay, Connor, what was your other answer? No, there's no tangential acceleration. Tangential acceleration implies, we're going at a steady rate, then we're going faster and faster and faster. So, that would be a no. And I skipped this. Let me throw that one in. I guess it was because it's checkpoint. What about alpha? Is there an angular acceleration? If angular speed is constant? No. Okay. Because these two are related. So no. There's no tangential, there's no alpha. All right. And then this part. If the angular speed is decreasing, so we were going around at a set speed, then maybe Lisa sticks her foot out to stop it, and it starts to slow down. Is there radial acceleration? Yes, there has to be. We're going in a circle at all. There is radial acceleration. What can you tell me is happening to that radial acceleration? It is getting less, because we know, well, where that originally came from. The smaller the speed, the smaller the centripetal acceleration. So yes, there is some, but it is decreasing. And what about tangential acceleration? Would there be any? Yes. And it would specifically be negative. Very good. Not too bad? Yet? Just kidding. Okay.